Thank you, Nico. Hi, everyone. I'm Alicia. I'm a software engineer here at SeatGeek. And I just wanted to, in the spirit of our workshop, where we're going to be delving into some more technical content thanks to Nico and Anna's amazing work, I also wanted to just give some of the general interviewing tips I would give to anyone starting out in software engineering, which is, there's just 5 up here. And these are just what I like to tell everyone, which is like confidence is really over-rewarded in tech. It's like kind of one of those things that for better or for worse, if you go in there with confidence, it's always going to help you come across better to your interviewer. And I always recommend to focus on just showing what a great colleague you would be, and don't get too caught up in technical details. Remember, the idea is to just show what a great team member you'd be. And one of the ways we do that is via our expertise in technical concepts, but there's a wide range of skills that software engineers need to bring to the table, including communication, teamwork, and collaboration. So just focus on that over every detail of the compiler errors or the algorithm. I always recommend to remember to keep talking or writing, whatever makes you more comfortable throughout the interview. Again, just keep externalizing those thoughts so your interviewer just has more to go on to want to hire you. The other one is listen to your interviewer. I think a lot of interviewers' pet peeves are if someone is struggling and they're trying to give them a hint about the problem and the person is so focused on their own thought process that they forget to hear the hint. And again, that shows how you can be a great collaborator and how you can work as a team if you're willing to listen to that feedback that the interviewer might be trying to give you as you work through the problem. And finally, I just think it's always really important, especially for people with marginalized genders in technology, to always be assessing the company as much as they're assessing you. Is this company a place where they will support you and make sure that you will thrive as a burgeoning software engineer? And that's just as important as impressing them and trying to get hired yourself. So I'm Alicia, once again. I'm a software engineer here at SeatGeek. Been here about a year now. I'm a back-end engineer on one of our e-commerce platforms here. If you want to get in touch with me, I have put my email there and my LinkedIn. So please feel free to contact me if you have any questions about SeatGeek. Really hope that some of you will apply to join, and we will see you soon.
Okay, great. It's fine. All right, everyone. Thank you for bearing with us during our technical difficulties. Now it's time for a lightning talk. Rachel is a Right Speak Code member, and we mentioned how we encourage our members to get involved in speaking and coding. And she's going to give a lightning talk that she's prepared for you. It's 5 minutes. Please give her your attention.
Hey. My name is Rachel. I am a back-end engineer, and I work primarily in Node. So this is going to be very JavaScript specific. A little disclaimer up front. This is going to assume that you have some knowledge about the JavaScript object literal and about hash map data structures. If you don't, now is a great time to catch up on email. And if you want to hit me up later, I'd love to talk to you about the basics of these things. So if you've ever used JavaScript or read JavaScript, you've definitely seen something like what we see on the left here. This is called the object literal notation. And if you write JavaScript, you know that this is something that we use to represent the hash map data structure in JavaScript really frequently. But in ECMAScript 2015, the spec introduced a new data type called map, which you'll see on the right. So that kind of begs the question, why do both of these things exist? There are obviously syntactic differences between the two, and those will make a lot of difference in kind of your enjoyment of writing them. But I'm going to not talk about those that much because enjoyment, who cares? The key practical differences when you're kind of choosing which one to use are pretty slim here. The key values are a lot more flexible in maps. You can use pretty much any JavaScript data type. It's easier to find your size, and it's an iterable data type, so you can use array-like methods on it. But the real meat of the differences happen when you get into how they handle prototype and compilation. So, starting off with the prototype. If you look into the map spec, you'll see that map is actually an implementation of the object literal. If you work a lot with JavaScript, this is not going to be super surprising to you because everything is an implementation of the object literal, including arrays and functions. But what that means for the object literal is that it has to be really flexible, and it has to have a lot of default information on it all the time. That information is stored in the prototype. And anything that is stored on the prototype is also implicitly a property of any object, which means that you have situations like we see on the left here. So we've got this cool array called dogs. We've got Spot, who is a good boy, and Sausage, who is a bad boy. If we look for Spot in dogs, he's there, yay. But if we also look for is prototype of in dogs, which is not one of our dog names, that is also there, because that is a utility method on every single object. This doesn't usually matter a lot, but if you want to do something pure, like implement a cache, you're going to have some issues because you're going to have key collisions. You can get around this sidebar by using this object.create constructor function and passing in a prototype value of null, but you probably don't want to do that because every single object that is a child of this object is going to inherit that prototype, and it's going to be really tough to work with them. Somebody on your team is going to be mad at you, or you're going to be mad at you in the future. The other big difference between a hash map and the object is how they're compiled. So we saw back here that we're kind of like already seeing differences between a pure hash map and the object literal. The way that objects are compiled in JavaScript is, and this is specifically in V8, which is the de facto standard. It's what powers Node, what powers Chromium, and everything that is built on top of Chromium, which is like half the web and a lot of your desktop apps. The way that objects are compiled by default is this fast compilation method, which is basically linear. And the way that it works is objects are converted into classes on the back end, and classes, every single property in an object is a class property in the C++. And the way that they're optimized is if you add new properties at runtime, an entire new class is built that is then linked to the original class, which is awesome if you have an object that's going to basically remain the same, but you can see how that would get really inefficient if you're going to be changing or adding values at runtime or deleting. So what V8 does is if you start adding a bunch of values or editing a bunch of values at runtime, or if you delete anything at all, it will drop you down to this dictionary compilation method, which is a hash map in C++. Essentially, it's just two large arrays, if you're really interested. But what will happen is you'll get transferred from this fast compilation method to the dictionary compilation method, which is a super expensive operation which you want to avoid at all costs. Before map, we didn't really have a way to avoid it because objects were always approached the first way and then downgraded. So the map data type lets you opt into this from the very beginning. So the upshot is there is now a optimized way to build maps in JavaScript, and you should use it if it makes sense for your project, and if it doesn't, you should just keep using objects. Thank you.
My name's Nico. I'm a software engineer and dev relations advocate. You can catch me talking tech, Code Switch on Twitter. I also do live coding and coding education streams on Twitch and Mixer. And I'm an organizer for Write Speak Code, hence my introing the event. So, it's my pleasure to introduce you to tree data structures. I will make this as gentle, as concise, and I swear as jargon-free as I can. And she looks nervous, and I think a lot of us can echo that feeling. Whether you are looking for your first role, or you're looking for your fifth role. But up till this point, navigating tricky computer science word problems wasn't how you thought that it would be determined if you were the right person for a role or not. But there is good news. One, it's not impossible to pick up these concepts. The second is if you look around the room, you're in good company. There are a lot of people who want to get better at this, so you have a support structure. And the third is that as engineers, finding solutions to challenging challenges is what we do, like, all day. So let's get this party started. with linear data structures. Here, I have a lovely array. There's no tricks about this array. It's an array with 6 integers. And I bring this up because when we're starting our coding journeys, we start interacting with data structures unconsciously. Arrays are life, and I feel like so much of how we learn how to boss computers around comes from us mangling strings. We reverse them, we remove letters, all these things with arrays. And then, as we get a little bit fancier, then stacks and queues. And what's important to know about linear data structures is that they operate in a sequence as if it were going through a list. And they have this concept of order, and that's why we can access what is first or what is the last thing in this stack, queue, or array. And final thing about them is there's no implied relationship between the data items that they're holding. We don't assume that 7 has any relation to 23, or that there's anything deeper behind it, or even that they're the same data type. Then we get to linked lists. Linked lists have something called nodes. And these nodes have 2 parts. They have data, which is represented by my letters here, and then each node has a pointer, and that pointer references the node that follows it. Even the final node in a linked list references something. It references null. If a linked list is entirely empty, then the head will point to null. So we had asked you to sort of brush up on the concept of linked lists prior to this, but this is just a little review. And it's so we can take this concept of nodes, and now we have a tree. This is our tree data structure. It still contains nodes. These nodes are still referencing nodes that follow it. The major difference is unlike the linear data structures that I just talked about, is they do represent the relationship between data items like a family tree. And like a family, this is where some of the jargon comes in. So, when we were talking about linked lists, we called the first node in a linked list the head. The first node in a tree is called the root. When a node references another node, for example, I'm just going to point. No, root is referencing these 2. Then those 2 nodes are considered its children, specifically its left and right child. And it is considered their parent. It's like this is where the whole family theme keeps coming in. If you look on the very final line of the tree, those are multiple children of the same parent. And just like in real life, children that share the same parent are siblings. And every node, every child node on the tree is a descendant of the root node. Okay, we're gonna take this whole tree concept a little bit deeper. So initially I was going to ask you to squint at the image on the left, but now you don't have to. You can just look at the image on the right. So our trees are actually turned upside down because the roots are at the top and the leaves are at the bottom. And leaves are the last nodes in a tree that don't have children. So in our example, C, D, and E are leaf nodes. This is the next part where jargon comes in. And in the next 3 definitions, whenever I use the term length, I'll be referring to the number of branches. So trees have height. This tree has a height of 2. And height is determined by the length, or by counting the number of branches between the root and the furthest leaf. So you're counting the distance to go from D to A. So 1 to get from D to B, 1 to get from B to A, 2. The height of a node is different. The height of a node is the length of a node, from a node to the deepest leaf. So the example of that is that B has a height of 1. Final bit of terminology is depth. And the depth of a node is the length from the root to a node. You don't have to drill this. This is something that senior engineers forget exactly which one height applies to, and they'll look it up. But we wanted you to at least have some introduction to this, so that as we go into the deeper concepts and you hear the terms, it's not totally foreign. So, what does a tree look like in real life? So, the DOM is a tree, for any of you who are familiar with HTML or web development. And it's a tree structure, and each node is an object representing part of the document. If you couldn't picture how that was a tree, bam, I got you. And this is that same code, but broken down into a tree structure. So the document is our root node. It has one child node, which is the HTML element. That HTML element has two child nodes, the head and the body. For those of you who don't do web dev, everything we see on a website is what's in the body. And body has two children, an H1, which is a header 1, and an unorganized list, which is a bulleted list. Those two children are siblings. And for our example, the text that is in our bulleted list of saying that Android and iOS are mobile operating systems are our leaves, or two of our leaves. If you didn't get that web-related example, here's another. And it's the concept of social media comments. Whether you are on Facebook, you have a blog, or on Twitter, we understand the concept that we put something out there, be it a status or a tweet, and that our friends and family, or strangers, they can comment on it. And other people can comment on those comments, and then we can reply to those comments, and then it keeps going and can get very complex. But this is another example of just a very simple blog with only 2 posts, and how commenting can also have this sort of tree-like form. And it gives you an introduction to binary trees and using them for decision making, which is at some point becomes what we use them for. Okay, so we just learned about trees. What's the difference between a tree and a binary tree, which is what we're here to learn about. And the difference is that tree data structures, nodes can have any number of children. But a binary, bi for 2, each child has 2 children at most. And it's referred to the left and right child, as I mentioned before. And binary trees can be balanced and unbalanced. This is one of the few where I don't have a lot to say. I want you to look at this. Look at these shapes. And you can see that the tree on the left is pretty symmetrical. Both sides, meaning if you were to cut it in half, and fold it like a piece of paper, the left and right sides are pretty symmetrical. Whereas the tree on my right is not. It looks like an upside down check mark. And the issue with this is that it starts to become inefficient. It starts to become slower. We don't want a tree that looks like this, but Anna will be going into why that matters. And we're actually at the end of your intro. This is your cheat sheet. I want to go over the concepts that we went over that you'll be hearing again in Anna's talk. And it's that the root is the topmost node of a tree, that parent nodes, they reference their child nodes through branches, that every child node has a parent, that a branch is how we link nodes in a tree, that leaves are the nodes in a tree that don't have children, and height and depth. How's everyone feeling? Are we okay? Do you feel 50% okay? 60% okay? Okay, I'm take that as 50. That's good. That's good. I'm gonna bring up Anna, and she is going to take us the rest of the way home with how to use these concepts to perform better.
Thank you, Nico, for intro. And we're going to use this terminology a lot today. My name is Anna, or Anna Leonenko. I am the co-founder of Esteem.com, which is a hiring agency, and the organizer of Write Speak Code, SeatGeek. Thank you very much for having us today. So binary trees. We already have met linked list. Thank you, Nico. Let's look precisely of the class of node in linked list. By the way, in all of the examples today, I'm going to use Java because first, it's my favorite language, and second, it's type safe. Every time I'm introducing new variable, I'm going to indicate what type is that. I think it's going to help us a lot. But everything I do can be simply translated in any other language. So the class node is interesting because it has a type of itself, variable of the type of itself next. Thank you for that. We can have our entire list as a reference to the head of the list and to the tail. How do you think? Can we build something similar for a tree? Yes, that's correct answer. How? Yeah, exactly. We can have very similar structure. We can define new class for the tree node and have two properties of the type of self, node left and node right. And the value. Value is very important. That's something we're going to use a lot. Here, I created two constructors just to create a simple tree in the next slide. First constructor only takes a value and creates a node, which pretty much is on the side of this slide, which has a value but doesn't have any children. And the second constructor takes a value, node left and node right, which both can be existing nodes, new nodes, or nulls. How does it look like? Pretty much that's it. That illustrates this simple code. Nothing bad, right? Everybody understands. All right. Now let's take a look at special type of tree, binary search tree. I think Nico already mentioned what is that. Somebody remembers? Anybody remembers? Okay, binary search tree is a binary tree where every value to the left of the node is smaller than the node's value, and all the values to the right of the node is greater. And that's true for every node. Now let's see how we can operate the binary search tree. Here, in this lecture, I'm going to use recursive approach because in most cases, it's much less code and simpler to understand. If you're not familiar with recursion yet, recursive function is the function which calls itself, maybe multiple times. Very important moment for recursion is to have a base case. A base case is a special condition. When we reach this condition, we're returning from recursion. If we forgot about that, what happens? Right, Stack overflow, because recursion calls itself until it reaches the limit of recursive stack. Okay. Let's try to go for a basic operation of binary search trees. First of them is search, and I suggest you to find a node 9 in this tree. How would we do that? We are starting usually with root, which is what node? 5, yeah. And how would we find node 9? We will compare the 5's value, which is 5, and 9, which is greater. 9, yeah. That means where are we going to go? To the right, right. If node 9 exists in this tree, it's going to be definitely to the right of the 5. OK, let's see if that's true. We went right. What we have met at the right? Node 8. Again, let's compare 8 and 9. What we're finding out? Greater, going right. Cool. And then we are going left. And we found 9. Wow. Cool. Let's look at the code. This is complete code for the search in binary search tree, which is recursive. If you're still not comfortable with recursion, don't worry. We're going to go through it right now. OK, from the search, we are returning the single node. That's why we are entering recursion here with the node 5. And let's look for value 3, if that exists. Entering here and assigning our output to some other tree node. I don't know why do we need that, but let's see. OK, when we first enter the recursion with the node 5 and value 3, inside of recursion, what do we meet? Base cases, yeah. 2 lines of base cases. We didn't forget about it here because we know what to do. First case is, yeah, if we hit null, that means that we found the special place for our node, but it's nothing there. What does it mean? Yeah, we don't have this value in this tree. And we're returning null. Fair, right? Second condition, if we found our value, we're just ready to return it. Wow. But right now, we are far from there. And what we want to do, we want to compare 5 and 3. And it depends on which is greater. We're choosing go left or go right. And where are we going? Left. Yeah, let's go left. And we are returning the output of the search function from the left subtree. And entering recursion again with the node 2 and the same value. We are still looking for a 3. Still no base cases, but now compare 2 and 3. Where are we going? Right. We are going right and entering recursion again with the node 3 and the value 3. And now, yoo-hoo, we found the value. We can return it. Great. Any questions? Yeah, everybody understands? Cool. Now, oh.
Why is this better than traversing an array?
We are going to cover complexity next, but if you want, we actually can do it now. So everybody knows what O notation is? Oh, great. So if somebody doesn't know, O notation is a way to define a complexity. Basically, it's when we approximately estimate the number of commands executed in this certain algorithm. If we are looking for a value in an ordered array, how many operations we would execute? How would we do that? With a for loop, right? And how many operations will be executed? And like the number proportional to the size of the array, right? How about ordered array? If we have ordered array, we can use binary search, and we can reach log n. Here is very similar to binary search. Have anyone noticed that? Yeah, so here we also have log n, which is pretty great. Right now, it's unclear why binary search tree is better than ordered array, but we are going to see it next when we find out what other operations look like. Okay. Any other questions? You are ready to code, right? All right, let's do it. let's find if the value exists in the array. In binary search tree. So we have binary search tree, and let's write a function which returns true if the value exists there, and false if the value is not in the binary search tree. And if you will do it too quick, please implement the same with iterative approach, which is not using recursion, only using while loop. 10 minutes for everything. Please come back to me. Let's discuss.
Hold on, I got it. Hey guys, we're gonna come back to the lecture. I hope you enjoyed interacting with the concepts that you just learned about. I hope that you were able to strategize with your table and with the mentors, which is half the battle. For a long time, when I saw a binary tree problem, I would just freeze up and it'd be like, I'm not getting this job, and sort of mentally give up. And that won't get us roles, will it? So now, Anna is going to take us through some of the next concepts.
Not yet. Let's discuss this first. Who got the recursive solution? Cool. Who got the iterative solution? Cool. Some people. Let's walk through it. So the recursive solution, yeah, I hid it what we've learned. Wanted to rely on your memory. That wasn't fair. But recursive approach is very similar to basic solution of the search. We are just replacing our returns of nodes or nulls with false and true. When we hit the empty space for our node, we hit false. And when we found our node, we return true. Who got this? Now. Cool, everybody, right? Right? Iterative approach is very similar also. Here, instead of recursion and calling itself, we define a while loop, and we travel left and right through this while loop, through our tree, and if we have met our node, we return true, found. If we hit the null, that means there is no of such node, and we return false. Nice. So one important thing, to rewrite your existing recursive solution in iterative way is very common thing on an interview. Why? You already answered that question. Let's answer it again. Why would we prefer sometimes iterative approach over the recursive? Because of Stack Overflow in recursive approach. So there is something which called recursive stack. When we use recursion, we are collecting all of our not returned calls in recursive stack. And this is just how it implemented in non-functional programming languages, which is a lot of languages. And the depth of the stack usually proportional to 1,000. In real-world bigger problems, using recursion in a big tree, which has million nodes, we just have a higher possibility of reaching this Stack Overflow. Iterative approach doesn't have it because when we travel with the while, we only have in operational memory one operation we are executing right now. Right? Right? Maybe I have mistaken now. You're sure? Okay. Let's see the next operation, insert. Oh, by the way, I forgot to tell something in my first part. Binary search trees. It's not something we usually can meet in wild. It's not something we represent by binary search tree, but we like binary search tree because we create it to store data, order it, and with better access, with good access by the operations of search, insert, and delete. And now let's dive into insert. In previous solution of search, we've been searching for a node, and we've been returning the found node. Here, we want to return the whole tree with inserted node. Let's insert this value, 3, into this tree, which doesn't have this value yet. Any guess how different would be the code? Well, yeah, when we are hitting the null, right? We are creating new node. Cool, yeah. Do we need this condition when we found our existing node here? No, because we're usually inserting a new node in a tree which doesn't contain it yet. By the way, in binary search tree, we don't have duplicates of the values. We only have 1, 3, 1, 1. In other trees, that's possible, but not in binary search. Okay, let's walk through the code. Again, here is a little bit different. We have the enter of our recursion here, and we're assigning the output of recursion to the root back. We are modifying this root. And what else is different? Who can tell what else is different? Not that many things, right? Yeah, we only have one base case if we found null. That means if we found the space where this value is supposed to be. Then let's create a node and return it right there. Also, never mind, let's walk through it. Let's return this recursion with the value with the node 5 and the value 3. And as we already know, where are we going? Left, yeah, we are going left. And now we are not returning from the left. We are assigning the output of insertion to this node dot left. That means 5 dot left will equal to the output of insert of the left subtree. Pretty cool, right? Who disagrees? Everybody agree, right? Great. Okay, we are entering recursion again with the value, or with the node. Which node? Again? Which node? Yeah, with the left node 2. Yeah, same value, going to the right, and assign to this node's right the output of insertion of the left subtree, which is what? We are not returning yet. We are entering recursion again with the null value. And here, we are ready to create our new node. Created. And then we are returning this node as an output of 2.right. You remember, right? And this subtree with the root of 2, we are returning as 5.left. You remember, we enter it at that point. And then we are returning our root as a root. Now we have the same pointer, the same tree, but now the value 3 exists there. Any questions? We already started to talk about complexity. Let's again remember ordered array, which has pretty good complexity for search, which is binary search. What if we want to insert some value in ordered array? What complexity would it take for us? N, right, because we want either copy the entire array to the new one with this value, or if we have bigger array, we want to shift all the values after the inserted one. How about the insertion here? What complexity would we have to insert value into the binary tree? Log n, yeah, because it's, again, binary search. Log n is way better than n, remember that. Here, we reached the point of understanding why binary trees can be preferred over the arrays. All right, any questions? Ready to code? Always ready? Great. 10 minutes for construct your own binary tree from ordered array. And I want this tree to be balanced, at least somehow. You may use the insertion function we just learned, or you may modify it. Doesn't matter. Both approaches can work. Who got a solution in pseudocode? Just understanding how to do that. Cool. No, 3 more minutes. No more time. Let's discuss. Somebody
Hi,
wants-
everyone. Anna is going to take you through how to complete this question. And she's going to, like, sort of see what levels of success we reached out here in the community. Anna?
Okay, who got an idea how to do that? Everybody? Everybody, cool. Who got pseudocode solution? Who got complete solution, recursive? I did. He did. Okay, few people. All right, why? Let's discuss it. What the idea? Who has an idea how to do that?
The trick is to recognize that the array is already sorted. So, you know, if you fold the strip,
If we go one by one, what we're gonna have?
you want to find the middle index of that array and use it and assign it to the root. And then whatever precedes the root index in the array, you're going to assign it to the left side of the tree, and the right side of the root in the array is going to populate the right side of the tree.
Yeah, great solution. Who had the same? Yeah, actually, in my understanding, this is the best solution. So we are dividing the array into 2 parts. Thank you for bringing it to the table.
Anya, the box is ready if you... Sorry, I didn't mean to scare you. But.
Thank you. Let's use it next time. So we're going to have a root, which is middle of the array. Let's then dive recursively to the left and to the right subarrays and have next level of these values. Then populate next levels again with the middles, and we only have few remaining. But this is not the only one, the only solution. Who has the other approach? You know that, right? I'm sure everybody heard about it, but for some reason, you're just not telling it out loud.
Are you looking for the way where we make a binary tree starting with the root of 1 and curl it all the way down with like the longest possible branches?
Well,
or do you want a better solution? Because I don't have a better
no,
solution.
better solution. This is good enough. We can find other solution.
Oh,
This
okay.
is not the only one.
So you can make a really bad binary tree where you make 1 your root and then make every other value a child of that node. So your left of 1 is null?
So
Like that,
you're
yeah.
suggesting to create this tree and rebalance that, right?
Yeah, don't
This
don't
is the
leave a
other
tree like
approach.
this, please.
This is no. This particular one would never be well balanced. But if we are skilled enough, we can rebalance such tree. It's not required in this workshop for sure, but this is another solution. Rebalance poor balanced tree. First, second, we just discussed. Separate array by middles. And this is complete recursive code for that. You can compare it with what you got. And the simplest solution also would be shuffle the array, right? I know somebody had this approach. I don't know why didn't you bring it to the table. All right. All right, so approaches can be different. And at the interview, you are not limited to what you have learned one day. You can be creative. Cool. Everybody understands the basic solution, right? Right? Say yes.
We have a question over here.
Hi. So you mentioned shuffling the array, but if your input is sorted, maybe some process wants
Maybe
it
it's
to be
for
sorted,
a reason, right?
So why would you shuffle it again?
Well, if you're solving real-world problem, you need to take into consideration everything around. But if you're solving algorithms problem, you don't have to care about something which is not set. All right. Let's go for deletion. Before we go for deletion, thank you, Jessica. Before we go for deletion, let's define some helper functions. First, let's discuss what's the minimal element in the binary search tree and how to find it. Which element is the minimal? The smallest one? 2. And where is that? It's on the left. Funny thing, the smallest element in entire binary search tree, doesn't matter which binary search tree is the leftmost element. How we can find it? You just go left. We go left and left and left until the next left is going to be null. That means we reach the leftmost element. And this is the minimal one. Pretty similar. What if we want to remove the minimal element? Only minimal element. What property, what condition is always true for leftmost element? Yes, and the other one? It comes from our helper function min. It doesn't have left child, right? Always, it only has right child. Correct? You agree? Cool. I like when people agree with me. I'm kidding. All right, so if the node only has its right child, and we want to remove this node, but we want to keep its children, what we could possibly do? How about to replace this node by its right child? Would it work? I think yes. Let's test it, in a case if I'm wrong. So here is the code. Let's walk through it. By the way, yes. No. Yes. 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 That's very good. I asked if everybody is agree. Who can repeat what Alicia just said and why it's true?
Okay, so when you're returning t.left, it has to be pass it into the function min, because it's recursive.
So yeah,
we're
we need to
looking for-
make this function recursive. In the way we have it right now, it only goes to the one turn and returning the left element, which works for this tree, but wouldn't work for any other. Yeah, we need to enter the recursion again in return statement. I'll fix it later. Thank you. Okay, but delete min should work. Let's test it. Okay. We are entering, by the way, everybody see the code clear? It's saturated enough? Okay. Entering recursion as we like to do that already with the tree node 5. Going to hitting our base case. What if our node that left already null? No, it's not there. If it's not there, we're just going further and assign to this node's left, which is 5 that left, the output from the delete minimum of its left subtree. And entering recursion again, this way, with the node 2, hitting our base case, and now we are ready to return this node's right as previous node's left, which is just replaces this node by its child. And now we are ready to return our root, but in this root, we don't have this minimal node anymore. All right, helper functions are here. Now let's remove something more complex. Here is complete code for deletion, but I don't want to go through entire code yet. I want to discuss something here. So what's in this code? Very similar to the insertion. We first trying to find the node we are deleting, and we don't just return this node, but we are assigning to the certain subtree the output of the previous deletion. We remember, it worked for insertion. At the end, we just returned the whole tree pointed to root, but restructured inside. Pretty cool. Here, I want to remove a couple of nodes. For example, the node 2. Node 2 doesn't have its right child. Similar to previous deletion, we can do what? If we're removing 2, what we can do? That's my favorite case. We are just replacing it by its child. It only has one child. Here, we can test it. If the node only has left child, let's just return its left. Should work. Worked at the previous slide, right? Should work here as well. What if we remove 8? It's here. Yeah, 8 also only has one child. Let's just replace it. And here is another condition. Bad thing happens if we want to remove 7. How to act in this case? 7 has right, left, and right has also children. I don't know how to deal with that. Any guess? Not from mentors? Okay, my suggestion. Oh, cool. We have, yes. Do we have mic? Could you pass the mic?
Oh, sorry. Yeah, sorry. I have a suggestion. So if you want to swap 7, I think you would do the minimum of its right subtree. So in this case, it would be 8. So you would keep recursing to the left here, and then swap those 2 out before you delete it. And then you would have to deal with the children of 8 too, but you would just keep moving it up recursively like that.
Yeah, very clear approach. So we need to restructure all the children of the 7 in the way to keep the binary search tree order and to replace it after. What we can do, we can take the minimal element in this subtree to the right, and it's gonna be the smaller than everybody to the right, but still bigger to anything to the left. We can assign to its right everything we had to the right besides this node, and to the left we can assign everything to the left of the node is being removed. Tricky moment, how we can restructure the entire subtree to the right of the 7 into the single node, into the single subtree we could assign to minimal dot right. Well, in this particular tree, that would work. So the approach was just replace 7 with 6. Yes, in this tree it would work, but if our node 6 had other children, what would we do in this case? Okay, let's discuss. So if we finally hit the node, found the node which has both children, and we want to remove this node, let's do that. Define temporary node and save the reference to our node which is being removed to this node. Then, to the current node, let's find a minimal element in the right subtree. In this subtree, this is the minimal element in the subtree to the right of the 7, here. 8, yeah. And we are finding it with the function minimum, right? We already know this function. We wrote it together. Okay, found. Then tricky moment. In the same operation, we are assigning to this node's right. This node already has right, but we ignore that. We are assigning to the node's right the output from the deletion, the minimal element, which is luckily the same element. That was a joke. We are not lucky. It's always the minimal element. It's the leftmost, right? Okay. we are assigning the output from deletion of minimum, which is the same node, to this node's right. Let's see precisely. Here our subtree. This is subtree 7.right. Let's remove the minimal element here. We are getting this subtree, 10, 9, 11. And then this subtree, we are just assigning as nodes left. Cool, we have pretty good subtree. And it has node.left free. To this node.left, we can assign something to the left, to the right. Which side is that? To the left of the 7, which is 6. Or the entire subtree, whatever is here, if 6 had a lot of children, all of them with the subtree rooted with 6 would go to the 8.left. And now we are ready to replace our 7 with our well-structured tree, which is very binary search. How would you like it? I love it. Cool. It's time to ask questions. Everything is clear. I knew that. Animation works. Okay, and now we are here in complexity. And we already know what is that. Okay, let's talk about it again, but I already told it to you. Now you told me, talking to me, right? Ordered array, search. Log, unordered array. Let's start from unordered, sorry. But ordered, that was correct. Log n. Unordered n, insert in unordered array. Well, here is tricky. It depends on our implementation of array. If you have array which is much bigger than amount of data, number of data, the insertion would be just 1. But normally we would have to resize. It would take another n. Delete. We need to first find it with n, right? And then delete with either 1 or n. N. Okay, I think I didn't cover it yet. We agreed, it's agreed actually, not we are, nobody asked us, but if we have a complexity of 2n, 4n, half n, 1000n, we consider it to be n. Why? Is that weird? A little bit, right? Actually, not really, when we're thinking about a large amount of data. So if our array is billion entries, items, it doesn't really count if it's 1 billion, 2 billion, or 3 billion. It counts when it's billion of billion, right? That's why everything which is significantly smaller than the size of the array, we just ignore. pretty convenient. I like to ignore that things. Okay, ordered array, search. You already know that. You just told me. Great. Insert. I would say n, yeah? We need to find a place with log n, and then we need to resize or restructure or shift whatever to fit the new entry into array. And in total, n. How would we delete from unordered array? Ordered, sorry. N. Linked list, better at some point. To search in linked list, yeah, it's unavoidable. We just go node by node until we find it. Insert, that's easy, yeah, just one. We just assign to the tail new node. Cool. Delete. Well, how about to find item to delete first? And yeah. Binary search tree. Search. Log n. Cool. Insert. Yes. So here is the question. Why would we need a balanced tree? So what if we go back to our ordered array in our tree? So here we are. How would it take it to find any value here in this binary search tree? And yeah, it's actually a linked list with some bonuses. With some defined bonuses, but not real. Yeah, so in average, in well-balanced tree or well-enough balanced tree, it's gonna be log n. And how about deletion in balanced tree? Log n, yeah. Again, we are just looking for it with something very similar to binary tree, and then removing. Cool. So what now is your choice between linked list, ordered array, and binary search tree? Cool. How about to code something else? Where is the excitement? Let's see if we have binary search tree. How about that? 2 minutes? 5? Okay, 10 minutes.
So the first thing you do is you check if your root is null, because if your root is null, you basically don't really have a tree. And then once you've determined that it's not null, you start comparing its children to it, and you ask, is the left less than the root or the node that you're working on? And if it is false, then it fails. And then you check all of your lefts in that same way. And anytime you hit one false, you're done. You don't have a tree, a binary search tree. If all of your left nodes pass, then you return to checking your right nodes. And if all of your right nodes pass, you still have a binary search tree. If any of your right nodes fail, you do not have a binary search tree.
Yeah, that's great, right? That's a very cool solution. So binary search tree is a tree where each node has to the left everything which is smaller and to the right everything which is bigger. I just can add one simple improvement. I would compare not to the root, but to the minimum and maximum value in subtree, because sometimes trees can get weird, and you can get the tree where the right child is the left child is less than the node, but greater than the root. Okay, with this small improvement, the final code would be like that. I forgot to change it from the long, but long is pretty much integer, but a bit longer. Okay, unfortunately, we reached the time limit here. We are just about to start traversals, which is really cool to understand. We probably will do it next time. But as a take-home, I really want you to take the solutions you got here and rewrite it in iterative way. Do you promise me to do that? Okay, cool. All right, Nico. So, okay, hackathon. All right. Thank you very much for being with me here today. I have some other problems here to take home, and also STEAM is organizing hackathon which targets the topic of equality. It's going to be remote. It's going to be June 27th to July 26th, and we're going to have great opening at one very good sponsors office who are, by the way, hiring from the hackathon. So join me there. Thank you.